Okay, hello everyone. Thanks for joining. I'm Jens Hertkorn. I'm working with ultra-cold quantum gases. And what we do every day in our lab by working with ultra-cold quantum gases is we confine atoms in some sort of potential and we image them with a high-resolution microscope that allows us to see individual atoms and really study how they interact with one another and how they are correlated with one another. And what I want to talk to you today about is the combination of two types of architectures. The first is quantum gas microscopy and how I'm building an architecture at MIT that combines it with programmability. So we're using fermions in the system. And in this new architecture I'm building, we are combining these two techniques to understand how many fermions interact with one another and particularly how they lead to interesting macroscopic behavior such as high-temperature superconductors and others that I talk about briefly. But first, I want to take a step further back and motivate this more broadly. So if you take a look around nature, you see that same structures occur in completely different systems, in completely different length scales, energy scales. And so if you, for example, in wildlife, chemical reactions, or in the outer crust of neutron stars. So if you want to understand why these structures occur in the same systems, you might have a difficult time studying the pufferfish and trying to understand what's happening in the outer crust of neutron stars. But there are some systems that are particularly flexible. For example, this is a classical ferrofluid. These are fine magnetic particles that are suspended in a fluid. And if you apply a magnetic field and you move it around, you can see it transitions through all sorts of phases, droplets, stripes, honeycombs. And so this sort of system is quite flexible to understand what causes the pattern formation in various systems. And so broadly speaking, the goal at MIT here for me is to build a quantum model system that can simulate various types of quantum systems. Now, there are different obstacles we have to overcome in doing quantum simulation. For example, if you want to understand how nuclei behave, they are very small, they are difficult to look at. If you want to understand how a neutron star behaves, an obstacle is that it's far away. And in between, things that we can have in our lab, like high-temperature superconductors, they contain particles that are really dense, and that makes them strongly correlated and very hard to understand. And this is where ultra-cold atomic gases come in. And really, Feynman's idea of doing quantum simulation comes into play. So the idea of quantum simulation is that if you want to understand a complicated quantum system that you have not good control over, you can replicate the quantum system somewhere else in your lab that you have better control over. And you can study this to understand the physics in the more complicated system. Now, if we talk about ultra-cold quantum gases, it might be useful to clarify what I mean by ultra-cold. This room is at a temperature of about 300 Kelvin, and the quantum gases we work at are down here at about 100 nanokelvin. So that's 1 billion times colder than this room, and these are the coldest objects that we know of in the universe. How do we get there? We use laser cooling tricks, and the path towards this has culminated in the award of several Nobel Prizes. And why we are interested in these ultra-cold quantum gases is you really start to see their fundamental quantum statistics, so their fundamental behavior of these different particles. There are two types of particles in the universe. There are bosons and fermions. Bosons are sort of social. They like to bunch up in the same quantum state. And this is fundamentally due to their symmetry property that I've illustrated here. If you swap two bosons, actually nothing changes. The wave function that describes the overall state stays the same. And so that makes them like to bunch up in the same quantum state. On the other hand, fermions are sort of antisocial. They have this strange antisymmetric property that if you take two fermions and you swap them, the overall state of the wave function gets a minus sign. So there is an exception to this. Fermions come in two flavors, which is called spin, for example. And if they are distinguishable, they have different spin, they could bunch up in the same quantum state. But really, for the purpose of this talk, it's important to know that two identical fermions with the same spin, they behave in this strange way. And to really focus on this a bit more clearly, what this means is if you take two fermions that are indistinguishable and you swap their positions, the state of the wave function has to change. And to make it even more extreme, I take the labels away. It essentially means that if you just take two fermions and you label them differently, you need to change the state of the system. So what does this fundamental property of fermions lead to and bosons? It leads to organization on a macroscopic scale. So what you can see here in a recent experiment by our group and also by Richard Fletcher's group is that these bosons really like to bunch up. We can trap them in space, and we can take a picture with a high-resolution microscope objective. And each of these dots here is a single atom that you can see. So even though there are not strong interactions in the system, you can see that they organize on a macroscopic scale. In this case, these atoms form a Bose-Einstein condensate, where all of them are in the exact same quantum state, and they start to behave like a giant matter wave. And that gives them interesting macroscopic properties, like superfluidity. On the other hand, for fermions, their fundamental symmetry property means that they are very hard to understand and very hard to simulate. And to focus a bit more on why they are hard to simulate, let's take really the most minimal example. Let's take one fermion that has 3 options. It has 3 different states it could be in. And we only have this rule that if we swap 2 fermions at their states, then the wave function has to change. But if we take one fermion and it has 3 states, well, it can occupy any of those. I can move it around. I can move it to the 2nd state. I can move it to the 3rd state. And really, to swap the state 1 to 3, nothing has changed in the system. I've just changed the state of the fermion. But if I include 2 fermions now, right away we have a bit of a trouble, which is we need to apply this rule that if we swap these 2 fermions, we need to have a minus sign in the wave function. So already in the 2nd step, we get this minus sign. And really, all we want to do is change the state of fermion 1 to the 3rd state. And so if we carry out the same procedure, we've done the same permutation. But you see, overall, the state of this wave function has changed with a minus sign. Even though we just wanted to involve state 1 and state 3, the mere presence of the atom in state 2 causes a wave function change. And if you extrapolate this a little bit more, if you imagine a chain of fermions from here to the moon, and you only have this fermion here and the last fermion on the moon, and now you want to know what happens if these 2 were reversed, you need to know the state of every single fermion between here and the moon in order to tell you whether there's a minus sign or whether there's no minus sign. So that makes it really hard. Now you might say, well, maybe you've just labeled them wrong. Maybe the atom on the moon is actually the 2nd fermion, and so you're just changing fermion 1 with fermion 2. But there is no ideal labeling, which you can see in a more concrete example. Let's take a few more and actually arrange them in a spatial grid, so they're not abstract states anymore, but they are on a 2-dimensional grid. Now, if you want to swap fermion 2 with fermion, or state 2 with state 3, you can do that, and nothing happens. They're neighboring. But if you want to swap another set of neighboring states, like 2 and 5, well, now I've chosen my labeling wrong. I need to involve what happens with all the fermions between 2 and 5. And so either way I label the fermions, there's one way I've done it wrong, or there's one way to exchange the states of the fermions. So there's no perfect labeling of these fermions. So this is the one part why fermions are hard. Now there's the second part why many are hard. And what do I mean by many? So if we just think of the number of possibilities these fermions can arrange in this 2D grid, you see the one I've drawn here can be in about 100 configuration. I can do that maybe on paper, maybe with my laptop. But if I just increase the number of by a factor of 5, we need to fill the memory of the largest supercomputer we have on Earth. And if you go higher by another factor of 5, you need the number of atoms in the universe to simulate or to store the state. So where are those strange particles? Where are the fermions? It turns out they're all around us. Neutrons are fermions, protons, electrons, and many atoms, they're all fermions. So if we want to understand how complex molecules behave, how the electrons in complex molecules move, if we want to understand what's the mechanism behind high-temperature superconductivity, or if you want to know what's happening inside a neutron star, you need to be able to understand somehow what many fermions are doing. And now there's this interesting idea by Richard Feynman is whether you can leverage fermions to simulate what happens in a many-body fermionic system. And one particular example I want to talk to you about briefly is one experiment that we have running in our labs, which is we take atoms and we trap them in a crystal structure made of light. So this is like an Hertkorn potential, and the atoms can sit in various positions. And they can hop between different sides of the optical lattice. We call this the hopping. And once they're on the same side, they can interact with a contact interaction that changes the state. Now we can take a picture of the atom's fluorescence picture, and we can study, because we have single atom resolution and also single spin resolution in the system, we can study correlations between all of these particles. And what we saw in this particular study is that these long-range correlations show that these fermions like to pair up, for example. And pairing is a fundamental property that you need to fulfill to form a superconductor. And for many decades, actually, people have believed that this Hubbard model is a good system to simulate what happens in high-temperature superconductors. But this search is still ongoing. I won't go into more details on this particular system, but I just want to highlight this is an analog way of doing quantum simulation of a complicated quantum system. But there's also a digital way you could think of. And this is what I'm building at MIT. So the idea has been proposed a few years back by Kitaev and Bravi. It's called fermionic quantum computation. And they asked the question, what do you need to leverage fermions for quantum computation? What are the ingredients you need? And it turns out you need to have either a fermion or no fermion, two different states. And you need to have three different actions that you can do on these fermions. You need to be able to apply a local potential. You need to have atoms tunnel between two states. And you need to have interactions between the two atoms. And so if you have these ingredients, you can leverage fermions for quantum computation. And this is what I'm building at MIT using a similar architecture, which involves high-resolution microscopy and an optical lattice to trap atoms in this Hertkorn potential. But importantly, we are incorporating tweezers, which is really tightly focused laser beams that allows you to pick up individual atoms and move them around. So if you go back to this analogy with the Earth and the Moon, if you were to swap the two particles, one on the Earth and one on the Moon, you would need, and you want to know how the state changes, you would need to know every single fermion between those two. But if you were to be able to pick up the fermion on the Moon and the one on the Earth, and you just swap them, you don't need to know anything between the two. Nature does it for you. So this is the idea of doing fermionic quantum computing. And I'm very excited to show you today how far we've gotten in building this machine, and some outlooks on what this machine will do and at which point we are at the moment. I want to highlight one difference to the quantum computers you might be familiar with, which operate with qubits that are not fermions. So in these systems, you also have two states. But if you want to make them behave like fermions, you need to program them so. Usually, qubits are distinguishable and they don't behave like fermions. So you can do some clever tricks programming them such that they behave like fermions. But you need more qubits for this, and you need deeper quantum circuits for this. On the other hand, if you use fermions and your two states are the presence or the absence of the fermion, you don't have this overhead. You can directly use them more efficiently for quantum computation of many-body fermion systems. So these abstract ideas that were proposed by Kitaev and Bravi a long time ago, they just imagined what if you could pick up these individual fermions and you could move them around, and it was an abstract idea. But over the last decade, these techniques have been developed. So we have optical tweezers that really allow us to pick up individual atoms and move them around. So we can exactly implement what they have proposed. We can trap a single atom, and we can turn up the power of the laser beam to apply a local potential. We can move the tweezers around by turning a frequency knob in our lab. And once they are in one side, we can turn the magnetic field knob, and that changes the interaction strength between the atoms. So we can implement the ingredients that Kitaev and Bravi proposed a long time ago. So what are the outlooks that we can pursue with this machine? We have tweezers, which are programmable, and we have an optical lattice, which is very homogeneous and a nice reservoir for the atoms to sit in. And these two fundamental ingredients help us to perform digital quantum computation. These are all new proposals that have just come out in the last 1 or 2 years. We established, sort of to say, a fermionic quantum computer with this platform. We can study particular fermionic quantum circuits. And there are novel ideas on how you could correct error in this quantum computing architecture. And if we have the first machine, or one of the first machines that can realize this, we can study which type of error-correcting codes are efficient and if there's more to be done. On the other hand, this programmability and moving atoms around also helps with analog quantum simulation, just preparing initial states better or faster or cooling the atoms faster. So this machine is really quite flexible in both aspects. Now I want to show you how far we've come. In the meantime, we started with an empty lab in about April 2025. And here you see our build-up process of the entire machine. And you might notice it looks quite small compared to the size of the optical table. And also, the entire assembly was done in roughly 2 days.
That's my birthday.
Oh, that's the birthday. On the birthday of the PI, even. So if we now compare this to a previous generation architecture, you see a typical cold atom lab that does all these things looks something like this. It's a table where you can barely reach a mirror in the center of the table because it's so crowded with optics and cables. And now in this new machine, you see Jacob, our grad student, is so happy to be in a next generation experiment. If you compare the length scale between these two experiments, we have compacted it to about maybe 10 to 20% of the optical table. And if we combine, so what are the ingredients we need to trap atoms in the system? We need to have an ultra-high vacuum chamber, first of all. This reaches the lowest pressures you can reach on Earth, roughly. This is a vacuum level comparable to outer space, roughly halfway between here and the moon. You need also some atoms. In our case, we use fermionic lithium atoms that we fill down here in a cup. And eventually, we have 2 microscope objectives that are used, one of them for imaging the atoms and the other one for projecting tweezers and other potentials onto the atoms. Now, if we take this machine and we combine it with cooling and trapping lasers, we can actually trap atoms. So this is how the system looks like in full action at the moment. And if you zoom in here in the middle, you see this interesting stripe. If we look into this viewport, you see actually the first lithium 2D mod that we realized at MIT. This bright stripe here are actually cold atoms. They have a temperature of about 100 microkelvin. And we can just trap them in the system and use them as a reservoir that loads the optical tweezers. So to give you a bit more intuitive picture of what's happening in this experiment, here's a close-up of the entire machine. And we start with atoms down here in the oven, which we heat. Now atoms fly up into this 2D mod chamber with the speed of the fastest fighter jets we have on Earth. We trap them here, and immediately within a few inches, they're slowed down to the speed of a casual pedestrian stroll. And after that, we push them with a laser where they move over quickly into this region where we catch them inside optical tweezers and inside another magneto-optical trap. And this is where we will manipulate them. So we are currently working on setting up this dual objective and tweezer architecture. And with this, I want to conclude that this entire machine is sort of a flexible system that allows you to do analog quantum simulation and digital quantum computation. And really, the entire machine is optimized to be quite fast. So all of this is done optically. There are no movable parts, no mechanical parts that need to be moved in order for the atoms to end up over here. And with this, I'm at the end of the talk. And I want to first and foremost thank Neil and Jane for supporting this project. It really wouldn't be able to start a completely new build of such a setup without incredibly generous support by Neil and Jane. And I also want to thank my entire group and the PI, Martin Zwierlein, who I've been working with closely over the 1.5 years at MIT. And with this, I'm open to questions.
Thanks, Jens. Questions? Okay.
Jens, you pointed out if you want to understand materials which have electrons, fermions inside, you should actually use fermions in your quantum simulation. Is there any simple model where you can quantify how big the advantage is? So in other words, if you have a certain system and you use a quantum computer which uses bosonic qubits, how much higher is the overhead to maybe enforce the anti-symmetry of fermions?
Yeah, thank you for the question. It's a really good question. Yes, there are systems where people are benchmarking this theoretically already. Typically, these are small molecules. So for example, lithium, hydrogen. You want to find the ground state of small molecules. And you can use the existing quantum computers to find the ground state of these molecules. And you can compare for a certain encoding. This encoding is called the Jordan-Wigner transform. If you apply this to make the qubits behave like fermions, then you can quantify the overhead that you would incur. And typically, this is on the order of n, where n is the number of qubits in the system. And there are more clever encodings. So actually, Kitaev and Bravi have proposed another encoding, the Kitaev-Bravi encoding, which brings this overhead down to log n. But still, it can be quite punishing as you are interested in larger molecules. And this is one way that people are currently doing it. But this is all happening on either a classical computer or on existing quantum computers that use normal atoms or qubits that are not fermions. So it would be interesting actually to find out what the real overhead is. There are also some proposals to interleave this fermionic encoding between normal quantum computation, which might also reduce the overhead for qubits. So people are, even in the regular qubit space, are interested in this quantum computing platform, and they want to minimize this overhead. So I think it will be interesting to see how big the overhead overall is. But in short, small molecules are currently the benchmark to see the overhead.
Other questions? They teach new faculty teaching presentations to just wait for, just not to fill the space, and someone will ask a question. So we're going to test that out. Sir.
I noticed in your images in the lab, there's quite a bit of what looks like probable aluminum foil. What purpose is that?
Oh yeah. It needs to be. We need to have an ultra vacuum system to prevent collisions of the atoms with background gas. And so you need to make sure that the inside of the vacuum system is extremely clean. Ideally, you don't do it in a dirty lab, but aluminum foil is extraordinarily good at keeping out the dirt. So if you actually are very meticulous in how you clean out the flanges of the vacuum system and you just cover it up with aluminum foil, you can resolve most of the problems.
Right.
Is there a concern with optical tweezers messing up quantum coherence when you're shuffling things around?
Yes, exactly. So this is a good question. Generally, yeah. Moving atoms and tweezers around requires you to have really fine control or have it characterized really well, and to equilibrate the depths of the optical tweezers. And so this is a generic problem, but this is where this hybrid architecture between a lattice and tweezers really helps out. So the lattice is just formed by a standing wave, by a retroreflected laser. And you can store the atoms inside this really nice, pristine environment without needing to form the optical lattice itself with tweezers. So it's sort of a nice storage location for atoms to prevent this.
Your computing involves moving things around.
Yeah.
It's
So
not going to work.
I think it's an interesting question. There have been early experiments that have created a Fermi-Hubbard model just with tweezers. It just includes careful calibration of the depth and the position of all the tweezers. And also, if you move them quickly, for example, lithium is quite helpful. If you move them quickly, lithium is helpful to mitigate noise that you have during the transport. So lithium is essentially the lightest atom you can have. There are also proposals to use excited helium, but lithium, for the most part, is an ideal atom to do this. And whether we destroy quantum coherence, we have to find out. But I think like the early experiments on Fermi-Hubbard models created with optical tweezers are quite promising.
Pablo?
So I know that a challenge is to cool down, because we're very cold, but not really as cold as we would like to be typically for to simulate many phases of quantum matter.
Yeah.
How is the progress in cooling down to what in solids would be actually low temperatures, for example?
Yeah. There's still progress being made. Very recently, for example, in Marcus Greiner's group at Harvard, they reach temperatures where you start to see antiferromagnetic order in the Hubbard model, for example. But I would say it's still generically a problem. How can you make the atoms colder. The most straightforward way of loading atoms into an optical lattice is just cooling them first and then turning on the lattice and letting them sit in the optical lattice. But most experiments have not incorporated lattices and tweezers. So we have hopes that combining these two enables new type of cooling techniques. For example, there's Raman cooling in an optical tweezer that we might explore. There's also expansion and compression techniques. You could expand the lattice, cool individual atoms, and then compress it. You can also bring individual atoms closer together and make them denser with the same temperature. So all of these are new avenues that we can explore with this machine. So hopefully to get colder in a programmable way, if you wish.
So you say ferromagnetism has been observed at Harvard. What is, how long will it take to see superconductivity, for instance? Do you have some forecast, to simulate superconductivity?
Yeah, it's...
for instance, in ITC, it was suggesting that you could model ITC superconductors. So
Yes. So I would say it's not totally clear that the bare bones Fermi-Hubbard model is the ideal model to study this, but there are new approaches that we're also following. For example, you could imagine having two layers. These cuprates typically have, and also the muthates have layered structures. So we use actually different layers to image spin up and spin down separately, but you can also keep the layers there and actually form more complex systems that are more similar to the high temperature superconductors we know. And looking there might be exciting for the future. I think in the bare single layer Fermi-Hubbard model, there might be issues that no matter how you cool them down, there might always be residual synglons that keep the temperature at a level that don't allow you to go to a high temperature superconducting state. And maybe with an extra degree of freedom with a bilayer, you could replicate a situation that's more similar to high temperature superconductors in reality.
thank you. Thank you very much.
Any more questions? Wolfgang?
This is a very ambitious experiment, and of course I know that designing and building a machine is a major accomplishment. But let me ask you, how long will it take to finish building the machine, and will you be able to do that before your fellowship ends?
That's a beautiful question. Thank you, Wolfgang. I would say most of the planning is actually done. It turns out if you just want to have atoms and tweezers, it's a fairly cheap and sort of simple endeavor to trap atoms and tweezers. And most of the planning is done, and we also have all the equipment. We have actually all of the spatial light modulators, we have digital micromirror devices, we have the high NA objectives, we have the cameras, all of this is done. And we're currently working on this. I would say we will have tweezers within about 2 months. And as soon as we have tweezers, as soon as we can play around with the programmability of this machine, we can start exploring, for example, cooling faster to Fermi-degenerate gas. I mean, how close we get to this ultimate goal and how good we are competing with Google, we'll have to just see. But interesting science can be done within the next 2 to 3 months, I would say.
Okay, we're going to stop there. Let's thank Jens again.